Thank you. Well, it's my pleasure to be here in this conference. Now it's time for a CO2 Spicer project from the Czech Republic. To be more precise about the soil gas monitoring there. First, please let me to briefly introduce you to the CO2 Spicer project at all. It's a pre-pilot CCS project in the Czech Republic. The true injection is planned to be in, let's say, 2028, 2030. As I said, it's a pilot of CCS in Czech Republic, so the plant injected amount is very small. It's only about 70,000 tons. Actually, we finished it months ago, so all the reports will be available soon. If you are interested about more about the CO2 Spicer, please visit the website down. It's quite easy to find it. And based on the VPs, you can imagine what was done. There is a 3D geological model. There was a dynamic modeling, also the geochemical characteristics and geochemistry, etc. And of course, the modeling was part of this project at all as well. I would like to say something about the target structure. We are located in southeast margin of the Czech Republic, very close to Slovakia and Austria, but still in Czech Republic. Concerning the reservoir structure, it's a fractured Jurassic dolomites. The field itself was discovered in 2001, so it's quite young. It's positive for us because there is quite new seismic data. There is also a lot of borehole data, etc., well logs. And actually, it's a major oil field with declining production. So there was a discussion what about next steps with this field, and it was selected as suitable for a pilot CCS project in Czech Republic. By the way, this is the field, quite nice landscape. There are two well hubs. It's not possible to see them from this part, but for example, people are likely that oil and production is there because of money to the budget, etc. So the public acceptance is quite nice, I think, there. Let's move to the monitoring of CO2 Spicer. The main aim was to prepare a storage site monitoring plan, of course, in accordance with the European and Czech legislation, according to storage of CO2 into rock structures. The site monitoring plan was based on the seismological monitoring, also the shallow groundwater monitoring and reservoir contaminant monitoring, but this presentation is only about soil gas monitoring. Well, as an introduction, soil gas monitoring is a suitable method for all terrestrial CO2 sites. The main aim, except of the storage site monitoring plan, was to determine the potential anomalies in situ, also to improve the knowledge about the seal efficiency. And we created several maps for the future conversion as a baseline maps to the injection monitoring and post-closure monitoring. We used, considering the methodology, we used two different approaches. The first one is a periodical monitoring 3 times a year using the EcoProbe 5 apparatus. It's possible to distinguish carbon dioxide, methane, oxygen, and also soil permeability. This is direct by the under pressure during the monitoring. And we measure the soil depth, soil gas from the depth of 80 centimeters. So it's a soil gas monitoring, not atmospheric one. The second approach is a continuous monitoring. We set every single hour the monitoring using 5 IGS probes. By the way, I see the same in your presentation yesterday, Stanley, so it's pretty nice if you are using the same devices. And of course, we selected several samples for a gas chromatography from each campaigns. Here you can see the monitoring grid of our field. We select 68 points above the field itself. You can see it on the left side of the screen. And on the right side, you can see also the 3D seismic cube and the 5 positions for IGS stations for a continuous monitoring. The field is quite small. It's, let's say, 1.5 kilometers across 800 meters. On this slide, you can see several pictures from the field monitoring. On the top, there is a periodical campaign when we drill the hole up to 80 centimeters to the soil and evaluate the soil gas in situ in each of these 95 points 3 times a year. And on the down of the slide, you can see the IGS stations continuous monitoring, just buried stations 1 meter below the surface and sometimes download the data, change the batteries, etc. Let's move to the results. Strong variability of CO2 content in soil gas was observed. Basically, CO2 in soil gas during the winter is very low. It's nearly half or 1% in soil gas compared to spring, where we see the big increase of amount of soil gas, CO2 in soil gas, and the maximum values were measured during the summer seasons. Here you can see the results from all 8 campaigns, the years as rows, and seasons as a columns. So there was 8 monitoring campaigns. What's great that similarities among the different years were observed. So the CO2 in soil gas, the patterns, it's somehow repeatable, which is quite nice. It's a nature, of course. The values are not the same, but it's repeatable. We can compare soil gas or CO2 in soil gas among the years. And you can see it here by labeled maximum values. Or there are several factors influencing the CO2 in soil gas. You can see that the 2021 average values are quite higher compared to 2022 because these years 21 and 23 were quite wet compared to 22, which was dry year. We believe that this is because of microbes activity, because of roots vegetation, etc., because of the vegetation fitness. Here is the results from continuous monitoring. It's a much more detailed data set across 3 years. To exclude the potential of the land use effects, the probes were buried to the grasslands. Again, you can see the maximum values during the summer seasons in 21, 22, and 23, compared to very low values of some of winter seasons, etc. This is important because the baseline, it's not, let's say, 6.5, it's one value. That's not true. The baseline is changing from time to time according to seasons, and there are much more factors. I will show some of them later. And of course, the baseline is different in different locations above the field. Let's move to the slide. Another slide. Here is continuous monitoring compared to weather conditions. As evident, one of the critical factor is soil wetness, or let's say rainfalls total. We see big increase of carbon dioxide in soil after strong rainfalls. So this is because of the roots respiration, because of vegetation, microbes activity, etc. Surprisingly, atmospheric pressure is not a strong factor as we expect. There are, let's say, small changes in sense of day-night, or hours. And of course, the most important is a seasonal, let's say, temperature or changing the seasons across the year. Again, concerning the factors, these 3 were evaluated as the most important. It's a seasonal vegetation because of respiration of the roots, rainfall total, and land use. We selected 3 categories, or we subdivided the land to the 3 categories. Those are grasslands, forest, and cultivated field. To compare them, fields are somehow heterogeneous compared to the grassland and forests, which has much stronger difference in content of CO2 above the field. You can see it here on this plot. Another possibility how to use soil gas monitoring is in case of existing boreholes. We select this one as for a risk monitoring. This was the second aim of this monitoring project. And the main aim was to evaluate it if the wells in the area are right or no about the leakage possibilities. We found only one increased value. These maps are concerning the methane, not the CO2. And the results is that the boreholes are tight with no leakage because of, let's say, 0 or nearly 0 values. It's possible to also get the isotopic composition if it's a light methane or a thermogenic one. Here is the same cross plots above the field, above the whole field. Again, no methane leaks from the reservoir were observed. The maximum values was less than 0.5%, which is quite normal. In this scale, it's ppm, not percent, of course. So the highest values is 0.5%. Let's move to the conclusions. We believe the soil gas monitoring is relatively cheap and suitable monitoring method for all terrestrial sites. In our case, concerning the Žarošice field, there is no leakage from the reservoir. Concerning the natural variability of the CO2 content in soil gas, we estimated 3 factors: seasonal vegetation, rainfalls, and land use. Important things that the similarities in patterns of CO2 in soil gas were observed. And we created several baseline maps which could be used for a future comparison during the injection and during the post-closure phase. Thanks for the attention.